welcome to the screencast where we will introduce the properties of the arctangent function. Let h be the function whose domain is all t values between negative pi over 2 and pi over 2 inclusive, and whose outputs are determined by h of t equals the tangent of t. We see in this graph that the tangent function is the dotted graph, and that h of t is only the solid piece of the graph, seen in black. Note well, because it has a different domain, only from negative pi over 2 to pi over 2, h is not the tangent function. Also notice that because the tangent function is periodic, it fails the horizontal line test, and the tangent function on its full domain does not have an inverse function. However, the graph of h, which is the tangent function with a restricted domain between negative pi over 2 and pi over 2, does pass the horizontal line test. That means we can consider an inverse function for the tangent function with a restricted domain. Looking at the graph of the restricted version of the tangent function as we defined it above, we see that the domain is all values of t between negative pi over 2 and pi over 2 inclusive, and that the range is all y values. In our previous study of inverse functions, we learned that their inputs and outputs are reversed. So we can say the domain of the inverse of the restricted tangent function is all y values, and the range is negative pi over 2 to pi over 2 inclusive. The restricted version of the tangent function we saw on the previous slide has an inverse function that we call the arctangent function. We formally define the arctangent function this way. Let y equal h of t equal the tangent of t be defined on the domain from negative pi over 2 to pi over 2 inclusive, and observe h takes angles between negative pi over 2 and pi over 2 and pairs them with outputs between negative infinity, infinity, or all real numbers. So for any real number y, the arctangent of y, denoted arctangent of y, is the angle t, where t is between negative pi over 2 and pi over 2 inclusive, such that the tangent of t equals y. We should remember that in the tangent of t equals y, t is an angle, and the output y actually represents the ratio of the y-coordinate to the x-coordinate on the unit circle. And since tangent of t equals y, we can also write t equals the arctangent of y. Notice that means the output of the arctangent function is t, an angle, and the input is a ratio of the y-coordinate to the x-coordinate on the unit circle. Because the arctangent function is the inverse of the restricted tangent function, all the properties of inverses we previously learned will be true. For example, we know that an inverse function reverses the process of the original function, and that y equals h of t and t equals h inverse of y say the same thing from different perspectives. So we know that y equals the tangent of t means that y is the tangent of the angle t. And if we change perspective, we can write the equivalent statements t equals arctangent of y, or t equals the inverse tangent of y, both of which mean t is an angle whose tangent is y. Another property of inverses we learned previously is that any point AB that lies on the graph of h of t equals y corresponds to the point B comma A that lies on the graph of t equals h inverse of y. For example, we know that pi over 4, 1 lies on the graph of the restricted tangent function, and we see that the corresponding point 1 comma pi over 4 lies on the inverse tangent function. So using function notation, we can say that the tangent of pi over 4 equals 1, which means 1 is the tangent of the angle pi over 4. Or we can switch perspective and we can also say that pi over 4 equals the arctangent of 1, or pi over 4 equals the inverse tangent of 1, both of which mean pi over 4 is the angle whose tangent is 1. Later, we'll practice evaluating the arctangent function, always keeping in mind that the arctangent function is defined in relation to the restricted domain of the tangent function, from negative pi over 2 to pi over 2 inclusive.